Hello once again, this is Skip, Victor Echo 6 Bravo Golf Tango. This video is kind of showing the second part of the 13 centimeter rack upgrade to the new Nextion display screens. You can see in this picture why I've already done the 23 centimeter rack upgrade on the right, and then the rack on the left at the top is the 13 centimeter transverter GPS upgrade I did last time. I started with the amplifier control shelf. First thing was to pull the old 4-line LCDs out and the older PIC control circuit boards, which are going to be upgraded for the new displays. Getting everything else disconnected and pulled off the front panel and it removed, it left quite a mess of wires. And like all the other upgrades to these displays, new PIC circuit boards were needed, so new printed circuit boards were designed and built. 6 all told, 4 for this shelf and then 2 for the dual driver shelf, which will be shown later. Then the joys of stressing my poor eyeballs again and drilling all the holes out with the number 69 drill bit. Then the boards were stuffed with the parts and stacked on standoffs and ready for mounting on the main assembly shelf. The original sequencer board is in the middle, with the 2 new boards on the outsides, left and right. Getting it all to fit was a bit of a challenge, but it all went together. Again, just like I did before, 3 mounting bezels were built out of thin aluminum. The bolts were attached with JB weld, and the new Nextion displays bolted to them nicely with plastic spacers. Next was enlarging the holes where the old 4-line LCDs were. I carefully cut the holes out from the back side because I didn't want to damage the paint or the labeling on the front of the panel. When I bolted the newly cut out front panel back onto the chassis, I realized just how close I was to not having the displays fit. I was relieved, I tell you. The hard part was finished, and now comes the fun part, I hope. So this shows what it looked like when I threw the power switch on. The 2 Nextion screens booted up into their splash displays. I tidied up the wiring a little bit and got ready to do some serious testing. This little video is going to show you the basic layout of the testing procedure. The 2 rheostats are going to vary current going through the small current sensor amplifier board. The function generator is going to simulate the pulses coming off a simulation of the flow meters. The little black box in the center there is what takes the current sensor data, converts it to serial data, and sends it over to the unit under test. Then, of course, there's lots of power supplies, lots of wires, lots of meters, lots of test leads that finally hook it all up over to the new upgraded shelf. To be able to test the temperature readouts, I had to connect cables from the unit under test along the floor and up into the racks, because the 2 water-cooled amplifiers are still in the rack, and that's where the Dallas temperature sensors are. So one more thing to hook up. So this is how it works. This is the splash screen when it first powers up. Touching the center of the screen anywhere brings you over to the main operating screen, and it's showing you here that the amplifier sequencer is enabled. The rest of the display is pretty straightforward, showing you the temperatures of the coolant tank, the amplifier temperatures, and indicating that the coolant flow is good with a pulse rate of 10. So at this point I'm lowering the frequency of the function generator, which is emulating the flow meter pulse rate. The incoming flow rate now is below the predetermined set point, and the unit for amplifier A disables the sequencer. So increasing the function generator frequency, the flow meter now is above the set point, and the sequencer goes back to enabled. Going over to this screen shows you where the set points are adjusted and where you can control the fans and the pumps. Simply by touching the text of what you want to adjust for a set point takes you into another screen. The set point numbers are simply adjusted up and down with the 2 push buttons. By going back and forth between these screens, all 4 set points are adjusted to whatever you want. The new values are shown, and then you hit the EEPROM button to save them in memory. As I've said before in some of my earlier videos, this is a much easier system than the way I had to do with the toggle switch for the LCD displays. Now if you want to turn the cooling fans on manually, you simply hit the button. Same goes for the water pumps. Just merely pushing the button on and off, and away you go. So that's all well and done. We flip over to the diagnostic screen. You can see here the two voltages that are being used, the 24 volts and the 12 volt displays. Also shown here is the 3 individual amplifier boards that are in each of the water-cooled chassis. It'd be pretty hard to have each amplifier display here hooked up to a sensor separately, so I have all 3 of them tied to the one current sensor board, and then I'm running the rheostats up and down just to confirm that the data is getting into it and the things are displaying. The test seems to be pretty good, so the next one along here is to check the receive transmit button. This is on there just so that I can flip it into transmit and look at the current draw when I want to. It's pretty well just a ordinary software switch, which ties right into the sequencer stage and puts everything into transmit mode, then back out again when I flip it back over to receive, as you can tell by the 2 colored LEDs on the front panel. That pretty well wraps up that test, so hitting the back button will take me back to the previous pages or screens. I did this for both sides, for both amplifier stages, and it was all good to go. Up to this point, the control stage previously here was fairly straightforward because this is practically a copy of the 23 centimeter amplifier. This next stage, though, the 13 centimeter dual driver, took some little more planning, a little trickier to get done. The one big job I had to do was cut these aluminum tabs off. I didn't have a whole lot of room inside this chassis. I couldn't mount the new display right in the middle. It had to be off to the side, and this metal tab was in the way, so I had to get aggressive. So I taped the rest of the chassis off to keep it from being contaminated, and used a die grinder and cut these tabs off, and everything fit. Just as before, the faceplate was taken off and the old LCD hole was enlarged for the Nextion bezel mount to fit into it. The new circuit board was mounted, and it was all ready to be rewired. So this is what it looks like when it was all rewired and ready to be tested. In this picture you can see that the 2 current sensors are mounted on this chassis, which made things a little different for testing. This unit being a little more self-contained than the power amplifiers, the cooling fans are mounted on this chassis also, so it's all in one box. So once again, there's more pre-testing to make sure that the circuits are all working before we can slap it all together. So again, here's another short video of the layout for testing. Done a little differently than before. The ohmmeter at the top is hooked to the one output of this shelf, which will indicate if the sequencer is enabled or disabled when it goes into alarm or out of alarm. I'm using my custom load tester here, which will pull current through the individual current sensors for checking them out. Then in the background you can see the 24 volt power supply being used, and the Visual Basic screens, which are connected also to this shelf for checking. Just like the other shelves, this is the main splash screen that starts up on, and then you touch it to get to the main operating display. Again, on this main operating screen, it's showing that the output to the sequencer is enabled, and the only other things that are being displayed are the temperatures for the driver amp board and the 2 main amplifier boards. There's no flow meter display because this isn't water cooled. The ohmmeter indicates that the line going to the sequencer is at a high state or open. So selecting now to go to the next screen, which is where the set points are and the fan on and off switch is, which you can see being operated and hearing the fans being turned on and off. There are two major set point adjustments on this shelf, the heat warning and a major heat warning. The heat warning is just a set point that will turn on the fan and let you know things are warming up but take no action. The major heat warning is when it'll shut the sequencer down and turn everything off. I'm going to try and simulate this condition by taking the set points and set the heat warning down below the operating temperature of the unit right now, which is around 19.5 degrees. By putting this set point down around 18 degrees centigrade, it'll put it below the normal temperature of what it's at right now, and we should get a heat warning. So moving back to the main operating screen, we'll notice that the sequencer is still enabled, but the fan has come on and we're getting the amp A and B heat warning. This is more or less just to turn the fan on and just a low-level indication that things are warming up. It's not supposed to shut anything down yet. So that part of the set point works. Now we'll adjust a major heat warning and see what happens. So it'll take a little ways to move this down. I've got to have it just above the normal heat warning and below the normal operating temperature of what the unit's at right now. So back through the pages to the main operating screen, and we can see that the sequencer is now disabled and we have a major heat alarm text coming up indicating what's happening. I move the camera up to the ohmmeter and you can see that line that goes to the sequencer is being pulled low to ground, which will shut the sequencer down and put everything in receive mode and everything in standby. Now I'll go back up to the set point page again and I'll take the major heat set point and set it up high, and it should go back into where the sequencer's mode is enabled, but the fan is still on. One thing I may change though is when I'm in these pages over here, if the fan has been activated in the main operating screen, it'll continue to run instead of going off as it's doing right now. There always seems to be lots of little adjustments or bugs you can work out of these things once you get them built until it's perfect the way you want it. So I've increased that major heat set point, and we see now we're back into having the sequencer enabled and the amplifier will be running. Now back to the heat warning set point, and we'll raise it up above the operating temperature of the unit, and the fan should go off and everything should be ready to go. Just like with the other shelf, I'll save these two set points into memory by pushing the EEPROM button, which shows that it's saved, and it'll be there until next time it's adjusted. So now back to the main operating screen, and we can see that the sequencer is enabled and the fan is not running, so see he's running cool and ready to run. Looking up the ohmmeter, you can see that the line that goes to the sequencer is above ground, so everything's enabled. The very last thing to test on this page is the fan control for turning it on manually. And as I push it, you can hear the fan coming on and going off. So moving onward with the testing, we switch over to the diagnostics page or screen and check out the functionality of it. On this page, you can see the two voltages coming in that run the amplifier, 12 volts and 24. And at this point, I'm adjusting the 12 volt power line so it goes below a certain set point and will trip an alarm. So back to the main operating screen, you can see that the sequencer has been disabled and it's telling me that there's a bad 12 volt power supply. I've increased the 12 volt supply up again and the sequencer is back to normal. The 24 volt supply monitoring works exactly the same way. Now we'll work our ways back to the diagnostics page and we'll make sure that the current sensors for the two amplifiers are working. I can only check one amplifier at a time here, so we'll be adjusting the current draw on amplifier B. I had to disconnect and hooked up to amplifier A to test it, but it also proved out well. The next and last test was for the page that indicates a RF output. These bar graphs indicating output power is just a calculated estimate of what the power would be. I know I'm going to have to recalibrate this when I get it back into the rack and under real operating conditions. But for now, it's a good test. This bar graph indication is working off the same current sensors as we've seen in a previous page. And it's just a simple math formula to give me a rough guesstimate of what the actual wattage is. Like I said before, it's going to have to be calibrated once I get it all in actual RF condition. This pretty well proves out that the new circuit is working. I just got to run serial data now out to the Visual Basic display and make sure that the information going to it is correct. On the Visual Basic screen here, it shows it's in transmit mode. That's because it's controlled by the sequencer and it's not hooked up to that part of the operation here. So we're just checking the two amplifier current displays to see that they're deflecting and matching up with the new Nextion screens. Finally, some real-time testing. I got everything strapped back into the racks and wired up, and we'll give it a whirl. So this is what it looks like. I got to say it's a lot better than the old 4-line LCD displays. I'm going to be firing up the transmitter and just into the RF dummy load for now, just to prove out that everything's hooked up and working for the next contest. So here's a closer view of the three screens. The top ones of the control shelf for the two water-cooled amplifiers and all the associated warning LEDs, and then below it is the one for the single dual driver. So everything looks good, the sequencer is enabled, and we'll go over to the next screen. So over here we'll do some functionality tests, make sure the fans are going on and off on the water-cooled amps and the dual driver itself. So the fans are coming on. We'll turn them back off again and let it sit in the automatic turn-on mode. Okay, next we'll go into the diagnostic screens and do a little transmitting. See on all three screens, the two top ones for the water-cooled amps, that the current is sitting practically at 0, and the dual driver itself is close to 0 amps, that is. I set it in transmit mode, and you can see the idling currents are right around 1 amp each. Keying the transmitter, now you can see the current is up to around 17 amps each, and on the driver right around 6 to 7 amps each. I switch over to the RF output screen on the dual driver to check the bar graphs display, see what they're doing. I keyed the transmitter and I see the bar graphs displays are going up. I haven't verified this part of it yet, so I won't say that this is what the actual output power of the driver stage is yet. So I'll switch back to the previous page on the driver here and flip back into receive mode. So I'll move back through the pages and get to the main operating panel or screen. And I might change this. I might put a button in there that takes me right back to page 1 instead of skipping through all of them to make things a little quicker. I'm going to key up the transmitter off with the microphone on the TS2000. You'll notice how the LEDs work. They're telling me what individual stage is being keyed. They come on slowly in transmit, but they go off real fast on going back to receive. That's just so I can hear the echoes for a quick turnaround. Notice on the dual driver screen that the heat warning is starting to flash. That tells me the temperature of the amps are getting close to the set point that has been adjusted. So we're almost done here. I brought the camera back away so I could check that the bar graph LEDs on the two amplifiers are working properly. Next, I'm going to swing the camera over to the computer screens to look at the Visual Basic displays and make sure that they're working, that the data is coming out of the back of the rack over to the computer for it. I'm using the transmit button on the touchscreen to activate the transmitter. You can see the bird watt meter there deflecting while I'm transmitting. I'm going to switch over to the screen that shows the 6 analog meters for the two water-cooled amplifiers, see how they're deflecting. So everything looks good for that part of the amplifier. Getting the data over to the screens there on the Visual Basic part. So that pretty well wraps up this part of the test. So we'll swing back over to the rack and shut things down. To shut this contraption down, what I usually do is switch off the 300 amp 24 volt power supply first. So this is a good test for this part of the alarm circuit. It comes up showing me that I have a bad 24 volt supply. Obviously, I turned it off. So in a condition like this, I would switch over to the 3 diagnostic screens and take a look at what's being shown, and it's 0 volts. The 24 volt power supply is common to all 3 circuits, so that's why it's reading 0 all around. Going back to the shutdown of this setup, next I would be turning off the water pumps to stop the coolant flow, and we'll see the indication there. You can hear the water pump noise going quiet, and see the top panels going into the alarm mode, or that the sequencer is being disabled. It shows there that the coolant flow is bad and the flow meter pulse rate is 0. Switch over to where the set point adjustments are, and you can see I have it set for anything below 10 pulses per second would put this thing into alarm mode and shut everything down. So if you're still with me here, I hope you haven't regretted the time you've lost watching all this. It's been kind of repetitious with all the previous projects, but I still found it interesting and a lot of fun. So thanks for watching. 73s.